Hello, YouTube. Hello, Zoom. Hello, Room. Let's revisit some old problems and some slightly more recent problems in the business of choosing a good route. I wrote a little bit of a preamble just by way of setting the scene. Um, so I don't know whether at high school you ever did kind of this sort of calculation where you're supposed to be proving an equation. So left-hand side equals right-hand side, and you work your way in small steps, each of which is justifiable to join up the left-hand side to the right-hand side. So calculation like this, where you might say, okay, well, something squared is the same as the thing times itself, and then you can multiply out and all of that kind of stuff. So just little steps, each of which is justifiable, that get you between two expressions that are too far away for one jump. And that's all that's going on with by route. It's the only rule we've met so far. So Ask has this concept of rules that allow you to make proofs. This is the root rule, and it's the only rule we use in semester one. There will be more rules in semester two. And all it says is that if you're trying to prove an equation left equals right, then you can choose something to put in the middle. And instead, you have to prove left equals middle and middle equals right. So that's to say, that's the ask way to make a step in a calculation like this. So it's unfamiliar notation, but I hope a familiar process of making an equational calculation, an equational explanation by taking steps. And usually, when you go by route, you choose a middle which is near one side. So quite often you might, it doesn't have to be the left, but you might think, okay, I know you choose a middle that you know how to get to from the left. So you should get one easy sub goal, left to middle, and then middle to right is the rest of the calculation. Okay, that's the situation. That's what we're doing. We're taking a step in a calculation, and we're looking for a step where we at least know the justification for one of the sub-goals. And we're hoping that the step we make is progress towards the other side of the equation. Okay? So then the real challenge is how to actually choose what step to take, right? You'll notice that Ask is not psychic. Ask can't figure out what you want to put in the middle, and that's why you have to say what to put in the middle. And so it then becomes a skill that you need to acquire. What's a good step to take in a calculation like this? And that's what we're going to try and get across more effectively in this lecture. It's not done by magic. There are strategies that you can deploy. And indeed, a lot of people not so far away from here, like in Edinburgh, basically, spent a lot of the 19 writing programs that could do this. And what they called that business at the time in the 1980s was artificial intelligence. And, I'm basically trying to teach you the strategies that those programs used to figure out what to do. So sooner or later, you might become as good at this as a 1980s AI. Fortunately for me, 2020's AI is bloody awful at doing this kind of stuff. It's embarrassing. They've got good chat, but no clue what's going on. In this respect, the intervening 40 years have seen a giant leap backwards, while the world is rather more on fire than it was back then. But, marvelous. Right. So let's see. It's fortunate that there's two of us because we can have a conversation about what we think is going on. So what I wanted to do was just get back to a problem we did some time ago and revisit it. So we're working with numbers. We've got plus, we got times, and I'm reminding you, you look at the way the functions are defined, you see which of their inputs they inspect, and that tells you how to poke an expression that involves that function to make computation a bit possible. That's to say, the why is it stuck thing. So plus wants to know about its first input, and the way we've defined it, times wants to know about its second input. And that's an accident of the way we chose to define these things rather than anything fundamental about addition or multiplication. That's just an outcome of these particular definitions. That, you'll always see the way the choices were made in the definition will show up in how the proofs work. Okay, so I'm throwing in that we already know that addition has a neutral element 0 and is associative and is commutative and has this lovely swap middle of 4 things. So swap middle of 4 basically says if you've got a square of 4 things to add up, you can add up the rows first or you can add up the columns first and you'll get the same answer. All right, so where we're going to arrive here is proving that multiplication by A is a monoid map from plus to plus. So that's to say, if you add stuff up and then multiply, you could have multiplied the individual things and added up afterwards. So we like monoid maps because they are a source of distributive laws. And we like distributive laws because they enable us to bubble things past each other when we're trying to solve equations. Okay, so can you give us a clue either, how do we start this proof? Inductively what? B is a good choice. Left-hand side is stuck because B plus C is stuck, and B plus C is stuck because B is stuck. Right-hand side is stuck because A times B is stuck, which is stuck because B is stuck. All the time, we're looking at the first input of plus, we're looking at the second input of times. You know what I mean by being stuck? I mean that there's a variable in the way where a function wants an actual constructor. The function needs to know 0 or successor, and here it's just got B, so it can't do anything. All right? So that's always the deal. Why are we stuck? So we got inductively, I forgot the D, inductively B, and then our objective here is to introduce enough case splitting to give us enough actual concrete data to make some computation happen. Whoops, I hit accept when I should have said send for form. Yes, you get all my favorite typos. Okay, so we are just doing the usual business. Right, we now have enough constructor information to get some computation happening. So we ask for the computation to happen by saying test. And at this point, we switch our brains back on. Okay, so that's the regular deal. You figure out what's going to reduce. You see, what's the point here? The point is that when the computation happens, we get a goal which exposes some recursive calls as part of the definition, which means that we are entitled to some induction hypotheses. So when we're thinking about a goal like this, there are several useful things to do. One thing I'm going to suggest we do is to put in all of the parentheses that ask has left out, right? Even though ask is saying, well, I know the BODMAS rules, so I know these parentheses don't need to be written. Um, it's sometimes helpful in order to figure out what's a good proof move to write the parentheses in. Okay, so we remember that plus associates to the left, so does times, and times has higher priority than plus. And that means what we've got is this, and this, and this, and this. So we can see all the clumps of stuff. Now, what I haven't changed the meaning of the goal. All I've done is made the optional parentheses visible.
But they're optional indeed.
Yes.
So another question on themes. Why do we need them? We don't need them other than for us to understand what the structure looks like this thing.
Yeah. Okay. So how do we strategize our next move? Step one is to take stock of what we know.
So probably we should write down the inductive hypothesis. Right?
Let's do that.
As a comment.
As a comment, yes.
Then we see what's happening.
So how do you do that? You literally make a copy of the goal, paste it into a comment, and then you replace the inductive variable by the thing that is known to be smaller than it. So you can see here, B is the successor of X, so we are entitled to know a version of the goal where B is replaced by X. So now we've got our induction hypothesis sitting there being handy. Okay, Clemens, do you see anything you like?
Well, probably. So if I now have the inductive hypothesis, I just look in the goal where I can see parts of the inductive hypothesis. And on the left-hand side, I can just see the left-hand side of the inductive hypothesis.
Right. Yeah, it's just sitting there. It's under the A plus, but it's there. The whole of the left-hand side of the induction hypothesis is sitting there in one piece. So we are entitled to switch it out for the right-hand side of the induction hypothesis. I also see some things I like. I like the fact that this A plus is kind of over to the left of the right hand of the right hand side. It's at the front of the right hand side of the goal. It's not at the top level because the bracketing's not very healthy. But we know we're allowed to muck about with the bracketing of addition. So that's at least promising. Okay? Moreover, I also like this A times X and this A times C because I recognize those as components that are showing up on the right-hand side of the induction hypothesis. Again, slightly annoyingly, they're not next to each other the way I'd like them to be, but they're at least in the right order, and all that we need is a bit of rebracketing of addition, and they'll be together. Okay? So that's three things. We recognize the left-hand side of the induction hypothesis. We recognize that there's an A plus somewhere we can dig out, and we recognize that there are two sub-expressions that appear in the inductive hypothesis that we would like to get nearer to each other. And any one of those three reasons would be enough to provoke the next move. The fact that all three of them provoke the same next move is kind of amazing. I mean, generally speaking, you see one side of the induction hypothesis in one piece on one side of the goal, and you go for it without even thinking harder. Right? Because it's usually a step in the right direction. So what are we doing? We are deleting the question mark because that's our favorite mistake. Not deleting the question mark. One of these days, I'll program ask to spot that you've left the question mark in and take it away for you quietly and spare your blushes. But we're going to choose a root. and I'm going to pick up the left-hand side of the goal, paste it in, and then I'm going to pick up the right-hand side of the induction hypothesis and select the left-hand side of the induction hypothesis and paste the right-hand side in instead. Okay, so what have I done? I've switched out one sub-expression from the left-hand side of the goal, and I've replaced it by a different sub-expression, or which is known to be equal. So that is a step I know I will be able to justify. Right. What's amazing is that I get only the left to middle sub-goal, which is to say, justify that step. And you can see I've got, as by design, I've got A plus left-hand side of induction hypothesis equals A plus right-hand side of induction hypothesis. So that's a straight up under plus. And the reason why we didn't get a middle to right is that it was a special case of the associativity of plus. So Ask was already happy to just do that rebracketing. It recognized that it was a direct instance of the associative law that we proved earlier. Okay, so do you see what's going on there? You take stock of what you know, you think, what does the induction hypothesis tell me? And what algebra do I know that enables me to move things past each other or to rearrange things to get us somewhere useful? And there, the induction hypothesis did most of the work, and we just needed a little bit of associativity of addition. Okay, cool. To channel Alistair, how do you feel about that? It's what I'm angling for is it's like, do you see why we chose the route we chose? Is that okay? Let's do another one. We said we were going to do this stuff if until past. Right. Okay. So next up, we've got associativity of multiplication. Right. So folks, how do we begin? What do we hit? Why is it stuck? Inductively C. We're always looking at the second input to multiplication. On the left, that's C. On the right, that's B times C. But then the second input of that times is also C. So that's 2 votes for C, no votes for anything else. So inductively C. From C. Fix up the ugly names. Okay, and then let's put the parentheses in. All right. And I think we should probably write down the induction hypothesis. Copy the goal. We know this time that X is smaller than C, so we replace C by X. And then we ask, do you see anything you like? So just, yeah, have a look. What do you like, Clemens?
I like A times B times X. because it's on the left-hand side of the proof.
Yes, it's right there, ready to go. And uh, I also like um, uh, I like the look of the fact that we've got A times on the right of the induction hypothesis, and that there's a B times X sitting there somewhere, but there's a B plus in the way. But we'll figure out what to do about that in a moment. However, Clemens has spotted a straightforward, just do it
Indeed.
by root. So I grab the part of the left-hand side that stays the same, and I paste in the right-hand side of the induction hypothesis. And already I'm thinking, I've got A times this plus A times that here, and I want A times this plus that. So I'm optimistic that I'll get from middle to right. I know I'm going to get from left to middle under plus. That will dig out the thing that we changed and justify by the induction hypothesis. But I'm also hopeful of getting from middle to right because that looks an awful lot like distributing multiplication over addition. So hoping that algebra is going to get us the rest of the way. And again, in fact, you see what happened, that the sub-goal we get is to justify the step we took by digging out the part of the left-hand side we changed. So it's very often that you find a by root is followed by a bunch of under just to reach in to the part of the expression that you rewrote and say, yes, that's the thing that we took. That's where we took the step. So that's all that's going on here is that this under plus is just digging out the place where we made a change. And we didn't actually need to do any work to get from middle to right, because that was exactly an instance of the distributive law we proved earlier. And that's why we proved it earlier, right? We prove these laws because they enable us, they give us more power to wangle the expressions that we're working with. We know that when we see, oh, these things aren't next to each other, I want them to be next to each other, that we want to be able to rebracket stuff or to distribute times through plus or all of these sorts of things. So the algebra is what we use to reduce the distance, the difference between the two sides of the equation. Okay, should we do the last one quickly? It's not past. All right, folks. What about this one? Why is it stuck? Pick a variable. C, good choice. It's the second input of the times on the left, and the right-hand side is stuck because A times C is stuck because C is stuck. So C is your friend. Terrible names. Right. Let's write out the induction hypothesis. And let's put some parentheses in that are implicitly there already. Although this will make the goal ugly. Just pull the box sideways. Okay. Um, do you see anything you like? I mean, do you see anything you like on the left-hand side? I mean, you got the left-hand side of the induction hypothesis right there. But you know, let's look ahead a little bit. We're adding up a bunch of stuff. We've got an A and a B, and you can see on the right-hand side, we've also got an A and a B, and some other bits and pieces. We've got an A times X and a B times X, and we can see that making use of the induction hypothesis is going to give us those bits and pieces. So, so this is a nice move. Uh, I mean, if you want to look at it the other way, I mean, we're again in the situation where there are multiple provocations, right? I'm looking at the left-hand side and seeing this A plus B. I'm looking at the right-hand side thinking, well, I've got an A and I've got a B, and I can jiggle around when I'm adding stuff up. I could get the A and the B next to each other if I do swap middle of four. And that would also get my A times X next to my B times X, which looks really quite good. So from the right-hand side, that's also a nice move. So again, multiple provocations for the same maneuver. And again, we're in a situation where middle to right is just swap middle of four, so we don't even see the sub goal, and we're left justifying the step we took under plus. Goodness me, it's just gone half past, and we've done 3 examples already. Okay, so folks, not magical, not magical in the slightest. Take stock of what you know. See, what do we know inductively? Ask yourself, does this get me any bits and pieces I like? You're just always looking for the sub-expressions that are knocking around. Think, is there any algebra that would get these things closer to where I need them to be? Okay. Um, so that's good.
It's a bit curious that Ask always needs help with the case that we thought was easy.
Yes.
And then does the magic with
Yeah, well, but it's usually just that we do a change that's underneath some other structure. We rewrite one sub-expression, so we have to dig out to that sub-expression with under to get asked to notice that that step's okay. I think version 2, I'm going to make that justification a little bit easier by allowing you to point to a particular sub-expression more effectively. Okay, so the plan is now that we do a more substantial thing just from a previous lecture. Right. So we did all this stuff with our new version of diff for formulae involving choose. And we just wrote down what was the case for plus and what was the case for times. And then we didn't even do the proofs. So I'm going to say, let's pretend we don't know the answer already and go back to here, undoing the plus and undoing the times. And then somewhere in this pile of proof, it's a bit of a monster. I'm going to give a little bit more space. And where are we? I'm going to delete that. So I'm just leaving it uh to test, and I'm going to delete that as if we don't know the definitions, because we now don't know the definitions. I'm going to hit send, and I'm going to hit accept. Okay. So you can see I'll make more space in a moment. Right. So this is our subgoal. Um, we haven't, so because we haven't defined this case of diff yet, that thing is stuck. We've got evaluate Q successor of N and evaluate R successor of N. So I'm going to do the thing that we've been doing of late, which is to copy the goal and make comments. Oh, that should be minus minus. Change P to Q. And another one with R instead of P. Okay. And I'm going to ask the usual question. Do you see anything you like? You know, what can you see on the left-hand side of the goal? Right? You can see the left-hand sides of the induction hypotheses. And if you look at the right-hand side of the goal, there's some stuff that we don't know what it is yet, but you can see a couple of bits and pieces, evaluate Qn and evaluate Rn, that we would love to see. We'd love to get those to appear on the left-hand side, because then we could cancel them. So you see, we got these pieces here. So that's the extra stuff that's on the right-hand side of the goal, apart from the thing that we're trying to define. So if we could make those terms appear on the left-hand side of the goal, then we could cancel them. And that would tell us what definition to make. See the game? So yeah, so what's our move? What's our route? I realize nobody likes a smart arse. Um, so it's you're waiting for me to tell you because you don't want to be caught thinking. I realize that, yeah, I mean, so this is the thing is when I was your age, I was not embarrassed by thinking. And that's because I've always been this strange. Um, you know, um, that's how I ended up where I am and the way I am, is I wasn't embarrassed by thinking. So you just look at what happened to me and you think, I'm not going to go there. None of this thinking for me. Um, you never know how you might end up. Um, so, uh, so yeah, this is an absolute classic. We can see intact in one piece on the left-hand side of the goal, the left-hand sides of both induction hypotheses. So I can see that they're going to introduce, because of this thing here, And this thing here, that's going to get me two of the things I want. They won't be next to each other, but not far off. And, and easily mangleable with the algebra we know. So, by root, and I'm just lining that up for a bit of pasting. Copy, the right-hand side of the induction hypothesis. The right-hand side of the other induction hypothesis.
I could place this desk for you better than me.
Cope. Right. Let's hit send. Okay. And accept what we got. So here, we've got something.
You left the question mark.
Oh yeah, fantastic. I'm going to click revert and remove the. Oh, okay.
There's still a question mark up there.
Yeah. Where?
Sorry.
You fix. Oh, right. Yes, that one.
Yeah,
That one.
Yes.
That's the evil question mark. Thanks, Clemens. Right. Hopefully this time something has happened.
Hopefully. Well, something has happened for sure, but
we've got two sub-goals. And the first sub-goal is what we're expecting as ever, which is to say, justify the step we took by digging out the changes. So that's under plus, exactly as plotted. So that's one thing taken care of. But now I'm writing the extra brackets in. Of course we do. All right. So now we know under plus is going to work. I'll not press send. You can see on the left-hand side, we've got two of the bits and pieces that we want, but we haven't got them where we want them. We're adding a bunch of things up, but they're not being added up in the order we'd like. We would like to get evaluate Qn to be next to evaluate Rn, because then we could use under to do a spot of cancellation. So here we're picking up the piece of algebra that's going to get the left-hand side nearer the right-hand side, which is a swap middle of 4 move. Right. So my motivation here, I'm thinking no further than I want to get this thing here, evaluate Qn, to be in the same place as it is on the right-hand side. So I'm asking, can I do enough algebra to do that? And I'll worry about what gets left over later. Okay, so I'm going to pick up, I'm going to write a set of brackets. Going to pick up the left-hand side of the goal. And then I'm actually going to swap the middle of 4. Pick this up, cut, paste, pick this up, cut, paste. So I know my move is justified from left to middle, because that is exactly a special case of swap middle of 4. Okay, so what sub-goals have come out? Uh, we only got one sub-goal, the left to middle, or the middle to right, because left to middle was already a special case of something we know. And now we've got this thing. Okay, write in the extra parentheses that ask is leaving out. And you can see that we have two pluses, a plus on each side of the equation. And moreover, the second input of each plus is exactly the same. So that's good news. Because plus allows cancelling. Yeah? Um, you know, the good move here is exactly to go under plus. Okay? And now we're left with a goal which we can't make any more progress on until we've actually done the definition. But this is a pretty big clue as to what the definition has to be. Whatever diff q plus r is, it has to give you the same answer as evaluating diff q and adding the result of evaluating diff r. So that rather strongly suggests that we should exactly define diff q plus r to be, you need an equal sign, diff q plus diff r. You hit send, and back comes the traditional rigmarole, which says, why did you waste your time on all of that nonsense? This is true already. Uh, you know, all of this stuff you did to figure out what definition to make is now true by definition. You know, take it away. I always quite like leaving it in. Uh, so there we go. You know, this by root business is absolutely not even remotely magic. Good moves include just filling in the extra parentheses that you're allowed to leave out by BODMAS, just so that you can see exactly the structure of what's going on and which things are really next to each other, which things you might need to do a bit of algebra to get next to each other. It's always good to write out the induction hypotheses in a comment and look for things you like. If you see one side of the induction hypothesis sitting there all in one piece in the goal, it's often a good move to switch it out for the other side. But you should be paying attention to which bits and pieces of expression you like and which bits of algebra you already know that you might be able to use to move things a bit nearer each other, right? You don't need to be sure that this is going to take you all the way from left to right. You just need to have a sense that you're making things slightly closer. So work little by little. I'm talking because I don't want to start doing the multiplication case right now. We don't have enough time for it. There's a little bit of there's what I've shown you will make the multiplication case work, but you can do it really nicely if you just stop and think a little bit harder. But I'm trying to give the general impression that although some thought is required, there is a whole bunch of reusable strategy. It's not that there's a miracle, brilliant flash of inspiration that has to be different every time. We're pulling the same tricks. We're saying, what's the induction hypothesis? Do I recognize it? Does it make progress? Do I have some algebra that will get me the rest of the way? So let's just apply those techniques and you will go a long way in this kind of proof. Okay, folks, I'll see some of you at 106, but the rest of you have a lovely weekend. I will be in Graham Hills 542 for the help session because I couldn't get me lovely Livy Tower room. All right, folks, cheerio YouTube, cheerio Zoom.
This 106.